Okay. Okay, Kamran, do you want to share your screen?
Sure. Can you see my screen now?
Yes. So
Cool.
our next speaker gonna be Kamran Pentland. He's a PhD from the MathSys CDT, and he will be talking about stochastic parareal, a novel application of probabilistic methods of time parallelisation. So Kamran, please.
Thanks, Ryan. So yeah, I'm going to talk briefly about the Powerreal algorithm and stochastic Powerreal that we've developed, which are essentially time parallel integration methods. So I'll just give you a brief structure of the talk. So I'm basically going to talk through some motivations and aims. So, you know, why bother doing what we're doing? I'll go through a brief overview of Powerreal. So this is an existing time parallel algorithm. Then I'll go through the stochastic Powerreal algorithm that we've developed sort of as an extension to Powerreal. I'll go over some preliminary results, basically to show that our idea works sort of numerically, and then I'll go through all the work that I still have to do for the rest of my PhD. So briefly, some motivations and aims. So why bother doing what we're doing? So essentially, we want to solve large systems of ODEs and PDEs. And I'm sure you've all found out the hard way that usually these can be quite computationally expensive, especially if you've got systems with a huge number of dimensions or a very long time interval. And even on HPC clusters, you know, they can tend to be quite slow. If you've got a PDE with a spatial component, you can parallelize the spatial domain. And, you know, these methods tend to be quite well studied, but again, they're tending to sort of reach scale-up limits. So you can't just keep throwing processes at your problem and hope that you get more and more speed up. You get different types of bottlenecks in speed that arise. And one of the ones that we're going to focus on is the bottleneck in the time dimension. So this kind of gives rise to the idea of a time parallel method. So what are they? They're essentially numerical methods that you use to integrate initial value problems by introducing parallelism, still can't say it, in the time domain. So it's quite counterintuitive because of the inherent sequential nature of time. So you've essentially got to solve for future solution states at the same time as current solution states when the future states depend on your current states. So no, it's quite sort of non-trivial as how to do this. So what are our aims? So the aims were basically to try and improve the speed up that we get from the existing sort of temporal discretization methods that exist in the literature. And 95% of these methods are deterministic, probably 99% of them are deterministic. So what we wanted to do is we wanted to sort of incorporate some sort of randomness or stochasticity, which is something that's yet to be exploited, and there may be a good reason as to why it hasn't been looked into, but we're gonna find out. And now the overall goal of this is long term. We basically want to apply these kinds of methods to speed up fusion plasma simulations. So my external partner, a few people that work at the fusion lab down in Culham in Oxfordshire, and they basically want to apply these kind of time parallel methods to speed up their plasma simulations. They've already sort of used the spatial decomposition methods, but now they want to explore the time domain. So basically, what have we done? So we've implemented and analyzed the Powerreal algorithm. So this is an existing algorithm that came out probably about 20 years ago. It's becoming quite popular, and it's actually quite robust, and it's been used to solve fusion plasma problems, molecular dynamics problems, fluid mechanics problems, among other things. And in response to this, we wanted to develop a stochastic version of this algorithm. So what we've done is we've analysed the performance of our stochastic version against this classical version by comparing the convergence rates. So if you don't take anything away from the talk, just remember that Powerreal essentially converges deterministically to a solution, and so its parallel speed up is basically fixed. So you have your problem, you apply Powerreal, and you get some sort of speed up that's faster than using a serial integration method. So what we basically want to do is we want to improve upon this deterministic convergence rate, but also maintaining the solution accuracy. But we do this by introducing some sort of randomness. So a brief overview of Powerreal. So we basically want to solve an initial value problem in parallel. We'll ignore PDEs for the moment because the spatial decomposition just sort of introduces more problems and can get quite complicated. So we just focus on an initial value problem that depends on time. We have an initial condition at t0, and we integrate over some interval capital T0 to capital Tn. And what you'd normally do is you take your integrator, your solver, and you integrate serially in time, step by step. Think about your classical fourth order Runge-Kutta methods. I'm not saying that they're necessarily slow, but you imagine if you stretch your time interval out long enough, it would take quite a long time to simulate your problem. So what Powerreal does is it essentially discretizes the problem into n subproblems on n subintervals, like you see in the picture here, and we assign each of these subintervals and subproblems a processor. So we have integration that's carried out by a slow integrator f at the fine resolution, so this sort of small time step, delta small t that you can see here. And then we also have a fast integrator g, which integrates the problem at a coarse resolution, so delta capital T. So essentially we can run g serially very fast over the entire time domain, but it's got a poor resolution. We want the fine resolution given by f, but we can't run f serially over the entire domain because it takes too long. Think about it taking days or something. And we can't actually run f in parallel on each of these subproblems unless we have n initial conditions. So we've got an initial condition at T0, but we have no initial condition at T1, T2, all the way up to Tn minus 1. So what Powerreal does is it essentially combines these two integrators f and g to determine the initial values in parallel. So I'll give you a brief overview of how it works. If we just think in one dimension at the moment, solving just a single ODE, we basically want to find the solution given by f over the entire time domain. So think about this black line here. This is just an artificial problem. This isn't an actual ODE or anything. So step one, we integrate using g serially. So we want to find the initial conditions at each subinterval. So we start from T0, going all the way up to T6. And what we now have is a very rough guess to the solution at T1, T2, T3, all the way up to T6. So what we can then do now is take the F solver and run it in parallel to find more accurate solutions. So you run it using these initial conditions, and you see between T0 and T1 that the fine solution has converged exactly as you would expect it would. But for all the other subintervals, they're not converged anywhere near the fine solution. So somehow we have to improve upon what they've given us. What Powerreal essentially does, the next step is it essentially goes back to the start of the time interval at T0, and you run the G solver again, so the fast solver. So you run it between T0 and T1, and you use this predictor corrector update rule, which basically takes the endpoint of each of the three solutions that you have in each time interval. So we take the F solution in the first interval and add it to the difference between the two coarse solutions, and that gives you this red dot here that you see at T1, which is called the predictor corrector solution. And you basically do this in each time subdomain. So we run G from that predictor corrector value, then we take the fine solution at T2 and add it to the difference between the two coarse solves to get the next Powerreal solution, and you keep doing this over the entire time domain, and you essentially get closer and closer to your fine solver. So essentially you keep repeating steps 2 and 3 until the difference between your successive iterations hits some required tolerance, and essentially all those red dots will converge towards the fine solution. What happens is the algorithm converges in what we call k iterations, but we're going to call it kd out of n iterations. And what happens is if kd equals n, so it's essentially like running the f solution in serial over the entire domain, so you basically get no speed up. So ideally, when you run Powerreal, you want kd to be much, much smaller than n, so that you get roughly a factor of n over kd speed up. So it takes 2 iterations to converge out of a total of 10. You get 10 over 2, so you get a 5 times speed up compared to just using the standard F solver on your initial value problem. So the algorithm's pretty robust already. It's deterministic. It's been proven to give good speed up and converges to the F solution. But can we beat this convergence rate KD? So if we take the classical Powerreal algorithm, at each subinterval, we basically have a single deterministic solution or initial value, and you feed it into your predictor corrector formula, and it spits out the next iteration, and so on and so on. The way that you can think about this predictor corrector rule is essentially it's a discretization of the Newton-Raphson method. So you basically give it an initial value, and in k steps, it gives you the root of your problem. So what we wanted to do with stochastic Powerreal was essentially sample m initial values randomly at each subinterval from some given probability distribution with a vector of means and some covariance matrix. And essentially we take all these m values at each subinterval and then we propagate them in parallel using f and g. And then from this complete ensemble of trajectories that we have, we basically pick the most optimal one, and then we feed those initial values into the predictor corrector and hopefully obtain faster convergence. The way you can think about it is basically giving this Newton-Raphson method a set of better initial conditions such that it converges in fewer than kd iterations. So just briefly again, so how does the algorithm work? So the first iteration is identical to Powerreal. So we're going to start from almost where we left off with these red dots, the Powerreal solutions. And what we do now is we take m samples at each subinterval from some probability distribution. For example, I've given a normal distribution here with a mean around the predictor corrector values, so around the red dots, with some finite standard deviation variance given by the difference between the two course solves. So if you can see, I don't know if you can see, at T2 and T3, you've got these purple dots that sort of cluster around the red predictor corrector values. So these are going to be our samples. So what we now do is we basically take all of these values and propagate them in parallel. And what we do is we propagate them using F, so you see the purple trajectories, and then we also use the course solver, so G, those are the yellow trajectories. So you should be able to see that on the sort of zoomed in figure on the right hand side. But we also take one of the samples we actually fix as the previous deterministic predictor corrector value that we had, just so that in the worst case, stochastic Powerreal should perform as Powerreal does. But we'll find out it's not actually quite the case a bit later on. So what we now need to do is we basically need to take this huge set of trajectories and basically pick the most continuous f trajectory throughout the time domain. This isn't quite the optimal solution. We haven't found a way of exactly sort of optimizing this process, but at the moment it seems to work quite well. So you basically start from T0, go to T1, pick the fine trajectory, T1 to T2, pick the best fine trajectory to the purple one at the top, and then at T2 to T3, we want to pick the most continuous one. So again, we pick the purple one at the top, and again, T3 to T4, the purple one at the top. And you also select its corresponding course solve, so the yellow curves as well. And essentially what we do is we replace the old predictor corrector values that we had at the previous time step with our new optimal samples that we're going to call alpha hat. And you feed those values into the predictor corrector, and essentially they give you the next Powerreal solutions at u k equals to 2. So you have the yellow dots that you can see now at each subinterval. So you do your error checks again, and if necessary, you do further iterations. The error check is exactly the same as what we had on the Powerreal slides. So I said we were going to sample these initial values from a normal distribution. So this was just one example. You can actually be quite flexible in what sort of sampling rule you choose. So we decided to go for 4 of these rules. So sampling rules 1 and 2 are normal distributions with different means. So the first has a mean around the fine solutions, which were those blue curves we saw back on the Powerreal slides. And then sampling rule 2 have a mean of around the predictor corrector values, so those red dots. And then we also considered sampling rules 3 and 4, which are essentially the same, but they're uniform distributions, but with the same corresponding means and variances as those rules above them. It's not too important, but we basically wanted to test whether the different sampling rules affected the performance of stochastic Powerreal. So to basically gauge whether stochastic Powerreal actually worked, we took a nonlinear ODE, which I found from some time parallel paper back in the 70s or 80s. You give it an initial value, u0 equal to 1. We want to integrate it over the interval 0 to 100. And what we do is we discretize the time domain, as we mentioned before. So we give it 40 time slices, so big subintervals, 80 course steps, 8,000 fine steps, and then we set the error tolerance to 10 to the minus 10. So we want it to be quite accurate. F and G were both selected as explicit fourth order Runge-Kutz methods. You can select usually whatever sort of time stepping method you like, but these are probably the easiest to implement at the moment. and we obviously gave G much larger time steps so that G runs a lot faster than F. And in the top right hand corner, you can see the solution that you get by solving the ODE. So you have the fine solution if we solved serially over in time, given by the black line, and then the stochastic parallel solution is given by the blue dots. So it fits quite nicely. If we run Powerreal itself, what we find is that it takes, as we mentioned before, it takes KD equal to 25 iterations out of 40 to converge. So this gives a rough sort of theoretical speed up of 40 over 25, which is about 1.6, versus a full serial F solve. So this shows that Powerreal gives a small speed up, but not a huge speed up. And if we run stochastic Powerreal now, if we take just 2 samples, so set M equals to 2, so we sample twice at each subinterval, and then we run stochastic Powerreal 10 times independently, what we find is on the right-hand side, at the bottom, you can see the convergence plots. So we have Powerreal given by the black line, and you see that it takes 25 iterations to converge. But if we look at the blue lines, which are the independent stochastic Powerreal runs, we see that it converges in anywhere between 15 and 20 iterations. So this is great. This basically shows that, you know, we're not crazy, the idea works. But the problem now is that because the algorithm itself is stochastic, the convergence rate K, which we'll call Ks for stochastic Powerreal, isn't actually fixed, and it's essentially almost like a random variable. So we basically need to measure how well it performs over a number of iterations. So this is what we did. So we essentially decided to find the distributions of convergence for each sampling rule. So sampling rules 1 to 4, and we ran the algorithm 2,000 times for each value of M given in the figure here on the right. So if we focus on the top left plot, so for sampling rule 1, so with probability 1, you see that if we set the number of samples equal to 1, this is essentially like running Powerreal itself, and the algorithm converges in Ks equals 25 iterations. So that's fixed for all time, no matter how many times you run the algorithm. But as we begin to increase M above 1, you see that the convergence rate drops immediately. So for example, for 2, you see the purple bars. With probability 1, stochastic Powerreal will converge in anywhere between 15 and 24 iterations. And then as you might expect, if you increase M further and further and further, that convergence rate continues to drop all the way down to, if you look at the blue bars, you can get an optimal value of Ks equal to 5. So that's a rough parallel speed up of, if we think back to the last slide, N over Ks, which is 40 over 5, so roughly 8 times speed up. So it's just quite a lot, quite significantly better than the 1.6 gain that we had from Powerreal. And all of these graphs look pretty similar. So it basically shows that sampling from a normal or uniform distribution for this particular problem didn't make too much difference, but it turns out that it does actually make a difference for other problems. So I'll just briefly summarize what we've been through. So for this system, and then basically other ones that we've tested, so we've tested a few 2D, 3D cases, we can actually better the convergence rate that we get from Powerreal. The convergence rate is actually, it's pretty dependent upon the type of problem that you're solving, so the dynamics of the particular system. So if there's chaos involved, or if there's limit cycles, the performance can vary a little bit. I didn't have time to go into that today, but that's something we hope to sort of narrow down. It also depends upon the time steps that you choose, the particular sampling rule, and obviously the number of samples that you take. Although I didn't actually show it, the solution accuracy is also maintained. So stochastic Powerreal generates stochastically varying solutions, but if you generate, say, 2,000 trajectories, they all cluster very, very closely together with a really small standard deviation close to the actual solution that you get by Powerreal. So the solution accuracy is actually maintained as well, which is nice. It inherits the properties of Powerreal. So again, it can solve systems that Powerreal has been proven to handle in the literature, which is something that was pretty key to why we wanted to use Powerreal in the first place, because it's been shown to be quite robust. But there are some systems that we're looking at where stochastic Powerreal can actually converge in more iterations than Powerreal itself. So we need to find a way of bounding this random variable Ks above by Kd, and at the moment that looks to be a little bit of a challenge. So we focus quite a lot on these iterations K, and not actually calculating the wall clock timings, because k is actually independent of the number of processors. I'm only limited to a certain number of processors I have here at Warwick, so I can't actually use thousands of processors to run these problems perfectly in parallel to calculate actual wall clock timings. And then looking to the future, so all this stuff that I still need to do, basically need to figure out whether this algorithm scales for much larger systems of equations. So when you discretize a PDE, sometimes you can end up with tens of thousands of ODEs. So is this going to work for those sorts of problems? It looks to be quite challenging. It proves that I've got a lot of work to do, but hopefully if it does work, then this could be quite a good result. The number of processors is also quite large, and it actually scales with m in our case. So Powerreal actually required n processors, whereas the stochastic version actually requires m times n processors, which can be quite an issue if you need to do quite a lot of sampling. So trying to optimize the sampling rule that we employ is also going to play a big part, because if we can minimize m, then we can minimize the number of processors that we use. And if this all pans out, hopefully I can write this up into something relatively publishable. And I think that's all I've got. So thanks for listening. If any of that was unclear, please do ask me. I'll stick around after the talk as well. So thanks again.
Okay, thank you very much. So before we went into the Q&A session, let's unmute ourselves and upload for Kamran's interesting talk, please. Recording now.